Start recording. All right. So we're on page 81, and we're looking at real gases. Up until now, we have only looked at ideal gases. So if you picture yourself riding on a little gas particle, here you are. Woo! Okay. Little smile. At the moment before it hits the wall of the container. Hi, Olivia. You wanted your test? Yeah, come on. There you go. You don't need a bubble sheet. You can just do it without, yeah. Okay, so we're just there and we are about to hit the wall of the container. At that instant, there are no more particles in front of you. Sorry, there are more particles behind your particle than there are in front of it, because that just makes sense. In an ideal gas with no attractions between particles, your particle would hit the wall with a force that depends only on that particle's mass and velocity. You need a periodic table? A pencil. Yes, I can do a pencil. There you go. Do you need a periodic table? You have one? Okay, cool. All right. So it depends only on that mass and velocity. So there's our ideal gas. Bam! In real gas, however, there are attractions. Okay, so if you have a real gas, there are attractions between the particles. They're not huge, but they are significant. Okay, and they will pull your particle back towards the center of the container. They're going to slow it down, and they're going to decrease the force and energy with which the particle collides with the wall. And you can see the BAM is smaller. BAM. Okay. So what does that mean? Well, what is pressure? Pressure is how much, or yes? Yeah, it's the force over P equals F over A, the force over a certain amount of area. And if we have less force with which they're colliding with the wall, then the real gas is going to have a smaller pressure than an ideal gas. Okay, so takeaway message, the pressure of a real gas is less than the pressure of an ideal gas. That's really the takeaway message there. It follows that the smaller the IMFs, the more ideal the gas will be. Yes, the pressure will be closer to the ideal pressure. The greater the IMFs, the less ideal. So, most ideal, helium. It has only 2 electrons in its cloud, so it's very unpolarizable. Okay, so most ideal, smallest IMFs. I think we're on page 82. Okay, only 2 electrons, it's a nonpolar. So the only forces it has are London forces, and it's only going to have the very weakest of London forces because it doesn't have very many electrons. N2, also nonpolar, but there is a larger electron cloud, so it's going to have slightly more London dispersion forces. And if we have SO2, can you guys draw a Lewis structure for SO2, please? And if you've forgotten, I'll help you out here. Hi. I am, but what would you like?
So for the test, do they have to memorize all the things on the image?
No.
Like the hydrogen side.
No. Just methane and ammonia. Yeah. Good stuff. All right. So we have, there we go. 2 electrons. Do you guys remember how to do Lewis structures? Hi. You are here to do the, what are you here to do? Remind me.
I'm here to catch up.
Okay. I have a tutorial session going on right now. So sadly, I cannot help you today.
Cool.
But can you come by at lunch?
No, I have a.
That's okay. Do you want to do tomorrow morning?
Oh, yeah, sure, sounds good.
Okay, cool.
All right, thank
Sorry about that. Electron, skeleton structure. And then remember, we add lone pairs until everyone has 8. What's the next step? Count electrons in the structure and compare. So let's see how many we have. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. What do? We say, I've got 20 electrons in my structure and I have 18 valence electrons available. We are going to have to do double bonds. Before we can double bond, what do we have to do? Yes, we have to erase a lone pair from the central atom. 1 pair too many. Erase lone pair from central atom. Okay, and now we have sulfur has only how many electrons? Sulfur has only 6, so we need to take this and move it in here. Yes? Okay, so when we do that, we now have O double bond S bond O. Okay. And is that a complete, are we done at that point? Resonance structures, okay? What's the SO bond order? Three over 2 or 1 and 1.5, okay? 3 over 2 or 1 and 1/2. I would tend to write it as 1.5. I don't know that they ever write it as 3 over 2. Ms. Chatross next door. 309. What? 1.5. Do you know why?
No, what's not again?
Okay, bond order is basically single bond, saying single bond is bond order 1, double bond is bond order 2. And so because we really have this pi bond is actually spread out over 2 areas, right? So 1 pi bond over 2 areas. So that's 1 over 2. So that's a half bond. So the sigma bond gives us a 1, And the 1 pi bond over 2 areas gives us a half. Or you can say I have 3 bonds spread out over 2 areas, which gives me 3 halves, and then make it into a 1.5. Yeah? And if we look at our structure, we have a lone pair here. So what shape does that give us? Bent. Yeah? What's the electron geometry? The electron geometry, we've got a lone pair here.
Here's
Is it linear?
right now.
How many electron domains do we have? We got 1 electron domain, 2 electron domains, 3 electron domains, yes? So because we got a lone pair, a bond site, and a bond site. So what we're going to have is we're going to have everything try to spread out as much as possible. Yeah, 3 electron domains gives us trigonal planar electron geometry. And therefore it is molecular geometry is bent. And what's our bond angle? Somewhat less than 120 degrees. But remember, on the AP exam, you can just say 120 because they don't care. They're like anywhere between 115 and 125. They're like this huge broad range they'll accept. So yes. No, because that's not a bond angle, right? Because there's no bond there. Yeah, bond angles are just between bonds. All right, so this is bent. Is this a polar or a non-polar molecule? Polar, and which direction does, well, I don't know which direction the dipole points, probably towards the lone pair, but I wouldn't guarantee that because oxygen is more electronegative than sulfur, but I still feel like a lone pair probably beats a couple of oxygens, but I don't know for sure. Doesn't matter, they won't ask you that. Okay? All right, so back here we have SO2, which is bent. So it is polar, and therefore we have dipole-dipole interactions, which are stronger than LDFs. Which means that once again, this is even less ideal. And then finally, we get to the least ideal, at least of these 4 things that we have, which is water. And that's because water has hydrogen bonding. And hydrogen bonding is the strongest of the IMFs, sort of up there with ion dipole. Okay? But you're not going to have to worry about that because you'll never have ion dipole bonding in a gas because there's no ions up there in the gas. Okay? So, little review there along with our new material. Second thing is that an ideal gas takes up no space. So the particles are considered to be like little points. So in an ideal gas, the particles are like so small they take up no room. But if we have a real gas, obviously real gases do have real volumes. And so if you get to a higher pressure, the volume of the gas particles becomes significant compared with the volume taken up by the gas. So there's less empty space compared with an ideal gas. Does that make sense? Okay, yes. Oh, it was just out of these. This isn't like most ideal of all and least ideal of all. It's just within these four. Does that make sense? Yeah. They're just examples. Yeah, yeah. So they're not going to have you compare those because that's kind of ridiculous. Yeah. Okay, so you can increase the pressure by either decreasing the volume as shown above or by adding more moles of gas to the container. That sound right? Okay. When you do either of these, so whether you compress it, like we show here, or whether you add more gas to the container, a real gas, the volume taken up by the particles is larger than you would expect from ideal predictions. So the volume of a real gas is greater than the volume of an ideal gas. Yeah? And the ideal gas is the empty space alone. And this is the empty space plus the gas particles. Do I think they're going to ask you about real gases? Probably not. But, I've seen it. So, real gases deviate from ideal behavior because there are intermolecular forces and they do take up space. And those are the takeaway messages. Okay? Okay, I found this somewhere and I kind of liked it. I'm not sure that it's helpful, but let's go through it anyway, because at one point I thought it was a good idea. So if we decrease the temperature, why pressure deviates? This is why pressure deviates from ideal pressure. You can decrease pressure by decreasing volume. Or sorry, you can decrease pressure by decreasing temperature. Does that sound right? Okay. If we decrease the temperature, the average velocity of the gas particles is lower, and that decreases the chance of an attraction being broken. Yes? It also increases the chance of an attraction forming if the particles are moving more slowly. Does that make sense? So if particles are moving past each other, the chance of an attraction forming are quite low because they're just going to fly past each other. But if they're moving slowly, they might be like, ooh, right? Okay. So we end up with more and stronger attractions between particles. And therefore, just before the particle hits a wall, there's a greater pullback towards the center of the container, decreased force per collision, which is decreased pressure compared to the pressure when there are no attractions between the particles. So P real is less than P ideal, which is basically what we said on the first page, right? We're just like, there are attractions, so it gets lower. And when we decrease the temperature, it is the decreased speed of the particles that makes it less ideal because the attractions are greater. Yeah. Now, we can also do it by increasing the number. We can increase pressure by increasing the number of gas particles or decreasing the volume. Either way, you're going to end up with more gas particles per volume. Yes? Decreased average distance means you're going to get stronger attractions between the particles, which means there's going to be less force, which means the pressure is less than ideal pressure. Is good? Okay. I was right. This did kind of make sense. Okay. Why does real volume deviate from ideal volume? You can either increase the moles of gas, or you can decrease the volume, which means you have a higher concentration of the gas, which means you have an increased percent of the total volume is occupied by the particles. So you're going to have a greater difference between V empty plus V particles, which is the real volume, and the ideal volume, which is just the volume of the empty space, which is basically what we said before. Okay. So we know that gases behave more ideally. You remember here, we could make them less ideal when we decrease the temperature, and we can make them less ideal when we decrease the, when we increase the pressure. So if they are less ideal at low temperature and high pressure, they will be most ideal at high temperature and low pressure. And if you have trouble remembering that, you can remember this little mnemonic device, plow thigh. So we have a little picture here somewhere. Where did it go? Oh, we learned this earlier. There was a little picture with like somebody like walking with the little plow. Let's see, where was it? Oh, I can't remember. It doesn't matter. Anyway, pressure low, temperature high. It's in there somewhere. There's a peasant pushing the plow, and you have to have strong, what page is that? Or 19? Oh yeah, that's the one with Mr. Miyagi as well. There you go. Temperature is high and pressure is low. Okay? Hopefully you won't even need that, because you'll just think, oh, if those particles are moving fast, they won't attract each other a lot. And if my pressure is low, the particles are not so close to each other, so they will, you know, not attract each other as much. Okay, where did we go? There we are. Okay. I think this is just going over the same thing again. So feel free to like read through it. When the particles are far apart, the IMFs are weaker. This is page 84. Okay. And you can actually see we have a little illustration here. So if we have fewer particles, we have less attraction. If we have more particles, we have more attraction. Okay. Here's our ideal gas at low temperature, high temperature to low temperature. So when we decrease the kinetic energy, it has no impact on IMFs, because ideal gases don't have any. But you can see here our IMFs. When the particles are moving faster, the IMFs are smaller. When the particles are moving slower, the IMFs are bigger. Is good? Okay, and that's it. And you guys could do, for homework, question, just whatever, Page 76? Page 76. Okie dokie. Thank you guys very much. Olivia, don't worry if you can't finish. You can finish in class if you need to, okay? Olivia Lee, meet Olivia Lee. I'm like, hang on, didn't I just teach you last semester? And weren't you in grade 11? Yeah, yeah. And thank you. Perfect.